Okay, so starting out here with number 8, it says here that we have a curve that is drawn for us. Goes from 1 to 1 here, so we got 1 here, got 1 here. The curve itself is radical x plus radical y equals 1. And ultimately we're going to find the area of that region that's enclosed by the lines and curves. And the other two lines are the two axes, so ultimately we have that as our shaded region. So if we're going to find the area of it, we're going to, I guess, need to recognize that if we could write this function for y in terms of x, then we could just write an integral from 0 to 1 then, couldn't we? So if I were to solve this for y, I've got radical y equals 1 minus radical x. And then if I square both sides here, I'm going to get y equals 1 minus radical x all squared. And if I were to integrate then on 0 to 1, 1 minus radical x all squared dx, okay, then that right there would do it, wouldn't it? And does it say anywhere that this needs to be done analytically? So then that makes it a what? Calculator problem. We do our math 9. 1 minus square root of x. All squared. Get our answer, which is that. And again, recognize that you know, this could be done by hand here, but since it, you know, this, if it didn't say analytically, then it would ultimately be in the calculator part. So the decimal answer is acceptable here. So let's see, approximately 1.67, 0.167, I should say. Anything else on number 8? What else? All right. 20, we have this time a region that is bounded by the x-axis. So we have the x-axis, we have the curve 3x to the 4th, which ultimately has the shape, and the lines x equals 1 and x equals negative 1. So we have some on this side of the x-axis also. We have the lines x equals 1 and x equals 1 and x equals negative 1, and the x-axis. So again, if those are all the boundaries, then ultimately we're looking at this shape here. Okay, and so I'll draw that in a more zoomed in manner, I suppose, here. So ultimately we're going to get this. So here's our negative 1, here's our 1. So we're ultimately looking at that. So again, with the 3x to the 4th being a boundary, the x-axis being a boundary, we know 3x to the 4th goes through 0, 0 here, so we're going to have essentially two separate parts over here. Since 3x to the 4th is an even function, this is also going to have symmetry, so if we just found one of those, whatever we have to find, we can double it. Okay, keep that in mind. We also know that the boundaries are x equals negative 1 and x equals 1. Those are our other two boundary lines, so that means that we're dealing with just that shaded region. And with that shaded region, our job here, number 20, is to revolve that region about the x-axis. So with that, if I were to draw kind of, again, a zoomed in version of that, whether it be the left side or the right side, and again we can do either and then just double it. Bottom line is if we're going to go over the x-axis, it's going to be a vertical slice. And if this is the x-axis, then what shape is that vertical slice going to make? It's going to make it's perpendicular, so it's going to make a disc or a washer. Which one? It's a disc. Right up next to it, so that would make a disc here. Again, the other half of the disc would be on the other side of the x-axis. So we know that for the disc method, we're going to go from 0 to 1 of pi times the radius squared, and the radius here is the 3x to the 4th, isn't it? And once again, it doesn't say anything about analytically here. True? So we could do it analytically because it's an easy function, but bottom line is it's a calculator problem if it doesn't say analytically. So we ultimately have the integrand here, 9x to the 8th. and we get 1 out of that. So ultimately we get an answer of pi. Now remember, we did it from 0 to 1, so that's only half of it. So the other half we would ultimately get times 2. So our final answer then would be 2 pi. And ultimately it would be a volume here, so it would be, if they gave us units, it would be something cubed, feet cubed, meters cubed, whatever the case may be. Questions on number 20. What else? On 21, we have to set up several integrals, and the region is y squared equals 4x. Alright, so we have the volume of the solid by the parabola y squared equals 4x, and the line y equals x. And we know what the line y equals x looks like. Okay. And the parabola, x equals 1/4 y squared, if you will. We solve that for x. We ultimately, again, have a sideways parabola. It's going to open to the right. The gist of it is going to be something like that. And again, we're looking for the area enclosed by those two. So that's ultimately what my picture is going to look like. You can plot a few points here if you want to with an XY chart to see that that does go above the line y equals x, and that would be our boundary line here. And so if we're going to do part A, for instance, they ask us to do it around the x-axis. So if we do it around the x-axis, keep in mind that this is already solved for x in terms of y, so the best way to do it would probably be with a horizontal slice. Since we already have it solved for x, it's in terms of y. So I would use a horizontal slice if I were you. And if I do use a horizontal slice and I use the x-axis here as my revolving line, that makes it a shell then. Because they're parallel to each other. So if I set up my shell method, I'm going to go 2 pi. In the x direction, or in the y direction, I'm going to go from 0 to what? Well, we need to figure out that intersection point right there. So ultimately, if we set our equations equal to each other, we'd have a quarter y squared equals y, if you will. Because remember, this is the line y equals x, or x equals y. So if we want to find that y value here, we could determine that our answer here would be, if I were to put a 2 in here, what would the 2 give us? If I put 2 in here, I'd get 1, but then I'd have 2 over here, and that wouldn't work, would it? What about 4 here? 4 here would give us 16, right? So 16 times a quarter would be 4. And wouldn't I have 4 and 4 then? 4 would work on both sides. So ultimately, putting a 4 in here would give me 4 on this side. Putting a 4 in here would give me 16 times a quarter, which would be 4 on this side. So that would be the true sentence here. So that intersection point is y value 4. X value, of course, is 4 also, since it's on the line y equals x. Right, so that intersection point is 4, 4. And so that means that in our shell setup, we're going to go 0 to 4 because we're in the y direction. And that means that the next part is going to be the distance from the shell to the revolving line, which ultimately is that arrow distance that I just drew here. So how far is it from shell to revolving line? It's y. And then the height of the shell is going to be the right function minus the left function. So it's going to be y minus quarter y squared dy. And at that point, it becomes a calculator problem. Questions on the setup part?
Could you also use the washer method for that?
You could, but then you'd have to solve this for y and use x values, because the washer method here would have given us vertical slices. So, like I said, since it's already solved for x in terms of y, if it's already in y, I would probably write a horizontal slice. That way I don't have to manipulate any of the equations, but I want to. Part B says, how about the y-axis? Now, if we go around the y-axis, now what do I notice about my slice? My slice and the y-axis are perpendicular. So now wouldn't it be a washer problem? Still a horizontal slice here. So I'm still going 0 to 4. But this time it's a pi situation because it's going to be general washer setup is pi times outside radius squared minus inside radius squared. And in our case, what's the outside radius? The outside radius is the distance from the revolving line to the outside of the washer, which is ultimately, in our case, it's the function y equals x, or x equals y in our case, because we're doing it in y. So the outside radius would be y. The inside radius would be to the curve function, which is going to be quarter y squared. And ultimately from there, once again, it's a calculator problem. So I'll take that as your integrand. Integral from 0 to 4, multiply by pi, and that will be the correct setup for that one. Questions on the washer setup? Okay.
Wait, are your limits always the same way as the slices are?
Well, if you have a horizontal slice, then your limits are going to be in y. It's going to be in the y direction. If it's a vertical slice, it's going to be in the x direction. In this particular case, it's going to be 0 to 4 regardless, but it's 0 to 4 because of the y value 4, not because of the x value 4. So bottom line is the limits in the slice. Okay? If it's a horizontal slice, then we're dealing with y values.
No matter what axis it is.
Yes. If we're dealing with a vertical slice, then it's going to be x values.
So it's always like perpendicular to the...
Parallel and perpendicular has to do with whether it's washers or shells, what was created. Okay? The slice itself, okay, tells us whether we're dealing with x or y. Okay? The parallel and perpendicular tells us whether we get shells or washers or discs out of it. Anything else before we look at part C? Alright, so in part C, same region. Draw it a little bigger this time. And this time we're going to revolve it around the line x equals 4. So x equals 4 is right here. And again, if I have a horizontal slice, which again you could use a vertical slice here if you wanted to, but I would use horizontal since it's already solved for x. So that's what I would do. So bottom line though is if I go around this line, what do I notice about the slice and the revolving line? They are what? They're perpendicular. So again, it's going to be a what? Washer. So 0 to 4 or pi. And I'm going to tell you right now in the AP test, if there's a problem like this, you'd get a point just for having that part right. Just for recognizing it's washers and having the pi and the right limits. You get 1 point out of 9 on a pre-response question. So 11% of the problem you get right just for having that. So that's pretty good. Alright, so in terms of the washers here, the distance here is what we need for the outside radius. So how far is that? How far is it from this point right here to this point right here? Well, we just said a few minutes ago that that part right there, this distance was a quarter y squared. True? And so what would this distance be then over here? If this is a quarter y squared, how far is it to get to here then? It'd be 4 minus a quarter y squared. So we'd have 4 minus a quarter y squared in that parentheses. That's the outside radius in this case. The inside radius is this, which we already said that from here to here was y. So from here to here would be 4 minus y. So that would be my inside radius for this particular washer. And at that point, once again, it's a calculator problem. Questions on that washer setup? And then part D, line y equals 4. So this time we're going y equals 4. So if we do y equals 4, I'll just add it to this diagram up here. If we take this shape and revolve it around the line y equals 4, then our slice is parallel again. So if the slice is parallel, then it's going to be 0 to 4 of what out in front? 2 pi, because that would be a shell this time. Parallel slices give us shells. And this time we want the distance between the shell and the revolving line, and at this point we need that arrow distance that I had. We said on the earlier problem that this was y right here. So what would this arrow distance be in this diagram? It would be 4 minus y, wouldn't it? The top function minus the bottom, which is our slice. So 4 minus y would be the distance between the shell and the revolving line. And then the height of the shell, is that any different than what we did in the previous problem? The height of the shell is just going to be right minus left. So therefore it'd be y minus a quarter y squared dy. And that would do it. Questions on that one? Now, just as an aside, on the AP test, okay, there are no shell problems on the AP test. So if this problem were on the AP test, the question is, could we use shells since we know them? The answer to that is yes. If you know shells, you can use them. Okay? But if you didn't know shells, because it's not an AB topic, okay, couldn't we have made a vertical slice here? And just like I said, couldn't we have written the equation in terms of x instead of in terms of y and did washers for this one too? Sure. Okay, so you don't ever have to use shells on the AP test. However, like in this case, it's easier to use shells, so I would. Okay? And it's not going to be wrong if you use shells because they account for the fact that some people might teach that in an AB class. So it's not an official AB topic for, I don't really know why they wouldn't have it be, but it's not. So it is a BC topic though, so the BC test there's possible shell problems. Elizabeth?
Should we spin it at all, like, correlate to the AP test then?
Everything with shells.
Okay.
Yep. Honey?
Wait, for part C, could you just go over the radiuses again? Like the outside and the inside one?
Well, again, we're going from the distance from here to here. Is the outside radius from the outside of the washer, because remember the washer's going this way. So how far is it from here to here? Well, from here to here we said it was a quarter y squared. So how far is it from here to here then? If this whole distance is 4 and this is a quarter y squared, then wouldn't that leftover distance be 4 minus a quarter y squared? Same thing with the inside radius. It's y to get to here. How far to get over to here? 4 minus y. Because ultimately those two together, y and 4 minus y would make 4, wouldn't they? Because how far is it from here to here? Anything else on the setups for this one?
Wait, no, this one is on the inside one side. Like,
This is your washer, right?
yeah.
It's going to be revolved around this axis. Okay. So this is the outside of the washer, right? So just in general, how far is it from the y-axis to this line right here? So how far is it from here to here? Quarter y squared. So then how far would it be from here to here, which is the outside radius? 4 minus quarter y squared. Same thing here. How far is it from here to here? Y. So how far is it from here to here then? 4 minus y. Okay. Jeff?
How come like you're going sideways, but it's like a y value that determines it?
Remember those things that I just mentioned, a quarter y squared and y, those are equal to what?
The x.
They're equal to x. So aren't they actual x's that we're dealing with?
Or is it just in terms of y?
But they need to be in terms of y because we have a horizontal slice. Okay. So those are x values that we're putting in here. I mean, 4 minus quarter y squared is an x value. Okay. But ultimately it needs to be in terms of y because we have that horizontal slice. Good questions. What else? All right. What else from the chapter review?
24.
24. We have solid. It's in the base of solids in the region that's enclosed by the graphs of y equals sine x and y equals negative sine x from 0 to pi. So ultimately we have these two, if you will. So we're going from 0 to pi, sine x, negative sine x. And it says each cross-section perpendicular to the x-axis is a semicircle with a diameter connecting the two graphs. So ultimately we have, if I draw my slice perpendicular to the x-axis, it's going to come out of the paper at us as a semicircle. So, in general, remember what we're going to do is we're going to start out by writing down the formula for any semicircle, which is 1/2 pi r squared. And then see if we can come up with an expression for the radius here in terms of our functions. Well, what would the radius be here if I go from here to here? Well, the diameter would be sine x minus negative sine x. It would be 2 sine x, wouldn't it, to get from here to here, which would be the diameter of my circle. So the radius, wouldn't it just be simply sine x? So there's my formula in x for the area of that slice. And how do I find the area of all the slices, which ultimately is a volume? We write an integral. So we'll take pi over 2 out in front, 1/2 pi out in front, go from 0 to pi of our sine x all squared dx. And then from there it's what? Calculator problem. So key is issue is drawing a picture and being able to come up with an equation for the radius here. Okay. We know that the radius is from here to here, and what is that distance from here to here? It's sine x, which in turn is the opposite of what we just said a minute ago. That is, how come that's a y value, right? Well, what is sine x? Sine x is equal to what? It's y. Sine x is the y value. If we were to take whatever particular x that we're at right here and put it in for sine, we'd get a y value, wouldn't we? Anything else on the setup for that one? What else? 39, we have a equation given that says that we have a volume of a solid that between planes perpendicular to the x-axis between 0 and 6, and the cross sections are the squares whose base runs from the x-axis up the curve. Radical x plus radical y equals radical 6, and we want to find the volume of this said solid. So they've drawn a picture for us right there already. So bottom line here is that those shapes that we have, those orange shapes that they have drawn there, they're squares. So ultimately, we'd start with that, wouldn't we? And so our job here is to see, can we write an expression for the side length of this square? Well, the side length, remember, in 2 dimensions goes from, this being our curve, goes from 6 to 6, if you will. That right there is our side length, isn't it? So wouldn't the side length just be, if I were to solve this for y like I did that last one, I'd have radical y equals 6 radical 6, that is, minus radical x. And then if I squared both sides, I'd get radical 6 radical x all squared. Which, if I just wrote that as 6 minus x, I'd get hit by a big trout. Right? So don't do that. So ultimately that right there would be our height at that point right there, wouldn't it? If I were to pick some x, would the height be given by that expression right there? So that's not only the height, but it's also the side length of our square, isn't it? So that means the area of our square is going to be that squared, because again, that's our side length. So ultimately it would be radical 6 minus radical x to the what? 4. So there's the area of the square in question. And so how are we going to find the sum of all the areas of the squares, which ultimately gives us the volume of the solid? And integrate from 0 to 6. And again from there, calculate a problem. Questions on that one? Others? Chapter review. Alright, well, what I want you to do next then is find your practice test that's in your packet that I gave you. I'm going to give you the answers to that so that you have a few more problems that you can practice on here. So you may or may not have done all these, or either way, but I'm going to give you the answers now. So you should be, this page right here should say Test A, Chapter 7. I'll give you a minute to find that, and then I'll show you what the answers are. You can write these down if you didn't already do them. So I'll give you a few more practice problems for the test tomorrow. Okay, here we are. So we have, and as we go through these, I'll tell you which ones that you do not need to worry about, because there's some of these things in Chapter 7 that we did not do. So 1 is good, of course, so take a second to check those. Keep in mind the video is still on right now too, so if you don't get all this written down, you can watch it later and it'll be on there. So we got right when time is greater than 2, left between 0 and 2, stopped at 2. The part B here is the displacement, 65 over 3 meters, and the total distance traveled, 97 over 3 meters. Number 2, we have velocity graph, and it answers are x equals -4 for part B, and 13 for, or part A I should say, 13 for part B. And number 3, you set up proper integral there, and anti-differentiate. Actually, it doesn't say analytically, so you really don't need to anti-differentiate. You can just do a calculator once you set it up. It'll be 2183 billion. So everything's in billions of dollars here in this problem. Number 4, if you find the area of that shaded region, should be 96 over 5. And that one does say analytically, keep in mind, so that one would be one where you'd need to show the antiderivatives, plugging in the numbers here. Number 5 is an area problem also, and that one is 500 over 3. 6 is another area problem. You'll notice that 5 and 6 don't say analytically either, so those could be calculator problems. 6 should be letter C, the correct choice. So letter C for number 6. Number 7, you got a solid of revolution, should be 15.122. And you'll notice that they did theirs analytically. However, it doesn't say analytically, so you don't have to do it analytically. Just write the integral and find the answer with the calculator. Number 8 is a shell problem. You got 13 pi over 3 is the result there. Number 9 you cross out. 10 is out. 11 is out. 12 is out. 13 should be 48 inch-pounds. So Hooke's law problem. 13 is good to go. And then 14 and 15 are both out. So you're basically doing 1 through 8 and number 13 on that page. Can't remember if I had already told you which ones or not, but either way. Anyway, you know again. Alright. Hey, is there anybody that did any of those that has questions about it right now? Right? Okay, number 6, we have an equation here that says y equals radical x, and the line is 6 minus 2x. So if I do 6 minus 2x, I'm going to be up here, and I'm going to be going down this way. Okay. So ultimately, the area enclosed by those would be this area right here that I'm shading. Oh, it does say the x-axis, you're right. So actually, scratch that. So it's not that. It would be actually, I'll make it striped, if you will, there. Oh, it's actually that. I didn't see the x-axis part. So it's the y equals radical x. It's the line 6 minus 2x. And it's the x-axis. So it would be this striped region here that I have. And you'll notice that if I were to try to make a vertical slice here, what would my problem be if I made a vertical slice? A slice here and a slice here would have different tops, wouldn't they? So we have two choices here. We could find this area by making a horizontal slice instead, because we have a right side and a left side that would be the same throughout the region. Or we could take this x region and just do what? Split it into 2 parts. So it's really up to us how we proceed. You can do it either way. Doesn't really matter. The only problem with splitting it into 2 parts here is that we'd have 6 minus 2x equals radical x as our equation to solve to figure out what that x value was where they meet. And ultimately this is going to be a calculator problem. I'm pretty sure that's not a nice answer. I could be wrong, however. If I squared both sides, it's going to wind up being quadratic one way or another, so I'd probably find it with my calculator unless it says analytically, or if it was on the non-calculator part, I guess you'd have no choice. But if we find that point in question, you would have 6 minus 2x radical x. Graphed it, so there we are there. And if we do our intersection command, 2.25 actually turns out to be a fairly nice answer then, doesn't it? So 2.25, 2 1/4, actually be 9 quarters. So we'll write it as that for the time being. And double check here, if we did 9 quarters here, we would get 3 halves in this side. And if we put 9 quarters in here, we get 9 halves. 6 minus 9 halves, that'd be 12 halves, minus 9 halves would be 3 halves. So it is an exact answer, 9 quarters, which is nice. Okay. Right? But again, if it's on the calculator part, I probably wouldn't waste any time doing algebra here. I would find it that way and recognize that it is in fact a nice answer and recognize it that way. So that means my setup here would be integral wise, I'd go from 0 to 9 quarters of the first part. The top function here is the radical x curve. So that right there would give me the area of the left half of that region, wouldn't it? And then I'd add to that from 9 quarters to 3. How do I know it's 3? 6 minus 2 times 3 would give me 0, wouldn't it? So that 0 right there is at 3. So I'd go from 9 quarters to 3 of the other function, 6 minus 2x dx. And ultimately, from there, calculate a problem unless it says otherwise. So, now we do it. Questions on that setup? And again, just to illustrate the alternative way to do this, if we were to put a 9 fourths into this function, we know we'd get 3 halves, so we could have written this from 0 to 3 halves. We could have written it in y. And then we would have done the right function. And the right function, keep in mind, would be if it's y equals 6 minus 2x, we'd have to solve that. We'd get y minus 6 equals negative 2x. We'd get negative 1/2 y plus 3 equals x. So we could have done right function minus left function. The left function, remember, is y equals radical x, so that means it would be y squared equals x if we squared both sides. So if we did that integral, then what should we get compared to what we have here with these two? Should be exactly the same. So again, if you have extra time at the end and you have a problem like that, would it be worthwhile doing it both ways? Set it up with x's or y's, horizontal slice or vertical slice. Why not? You got extra time, might as well, right? Get it right both ways and get the same answer, you feel pretty good about it, I suppose. Any questions on any other part of number 6?
Can you split them up like that when 2 slices wouldn't be the same?
Well, if the 2 slices, in order to just have the same slice throughout, it had to have the same top throughout and the same bottom throughout. Since we have a different top here than we have here, that's going to make 2 totally different answers. But on if we did a horizontal slice, no matter where I drew a horizontal slice, the right would be the line, the left would be the parabola. So therefore, horizontal slice, we'd only need one integral. So if I drew it down there, I'd have line, parabola. If I drew it up here, it'd still be line on the right, parabola on the right, or line on the right, parabola on the left. What else? And 3, we have a s function at 6.22 times e to the 0.086t. And it tells us that this is a rate, which is kind of a giveaway here, and the fact that it's in billions dollars per year. And think about if we were to graph this s function, the y-coordinates here, which are s, are going to be in dollars per year. And keep in mind it's billions of dollars per year, but just for me not having the right billions, I'll just keep it like that. And the t here is in years, true? So whatever this function looks like, we know, essentially it's an exponential function. Okay, what is the area under this curve going to give us then? It's always going to give us dollars per year times years. It's always going to give us y values times x values, whatever those are. And so ultimately, wouldn't it give us total dollars? So with that said, the question that we're asked here is that from January 1st, 1950, find the total expenditures from that day to January 1st, 1990. So ultimately, if we did our integral here, our integrand is going to be the function because we know we want the area under that curve. So that part would be the integrand. And the only other issue is what are the limits going to be here? Well, if we call time 0 January 1st, 1950, what would be January 1st, 1990? It would be 40 years from that. So if we go from 0 to 40 of that, we'd get 2183, and that's in billions of dollars. I believe it was 2183 if I remember right.
Yep.
What else? Anything else in the practice test? Right?
Number 13.
And 13, remember with Hooke's law, we know that the force for any spring is given by force equals kx. And it says that the spring has a natural length, suppose a spring has a natural length of 8 inches. To extend the spring 2 inches, a force of 3 pounds is required. So that means if we do force 3 and we stretch it 2, that means that our 3/2 is going to be our k value for this particular spring. So that means our force equation is just simply 3/2 times x. And then ultimately, the question says how much work would be required to stretch the spring from its natural length to twice the natural length. Well, keep in mind that work done is always the integral of the force equation. Okay. So work done is always the integral of the force equation. Okay. If it's constant force, okay, then we can just use W equals Fd. Okay, because it's going to be a constant force. We don't need to worry about the fact that it's a variable force. But with a spring, it's a variable force. The further we stretch it out, okay, the more difficult it gets. Or the same thing, if we try to stretch a spring the other way, if we push a spring in, then what happens is we push it more and more, the spring gets more and more difficult to push, doesn't it? So that's why it's a variable force that's required to stretch and pull a spring, stretch and shrink a spring, if you will. Now the only other issue is here. What about my limits here? What was the natural length? 8, and it goes to double that. Would be 8 to what? 8 to 16. And again, from there, unless it says analytic, do the calculator. Like I said, some of these integrams are easy to do with the fundamental theorem, but if it doesn't say to do it analytic, why waste the time doing the antiderivative parts?
It gives you a different answer than what they have.
Let me check. What's it say?
Cause like, I
It's
got
48.
144.
Let me see here. So we got 1.5x, right? That what integrand you used? So 144, what did it say in there?
48.
Is it 48?
For the integral from 0 to a.
Oh, you know what? That's right. I messed that up on the 8 part. Anytime that we're dealing with any kind of spring situation, right, no matter what the natural length is, I guess the fact that they even gave you the natural length is kind of a side step for us. But bottom line is, if it's going from natural length to anything, start with 0 for your natural length. Okay, ultimately, the 8 to 16 that I did there, that would give the answer to go from essentially 16 to 24. Okay, because ultimately 0 is always going to represent the natural length. Okay, and so if we want to go double the natural length, we don't want to use 16. We use 8 here. Remember, 8 more would be double the natural length. So that's why it should be 0 to 8. So just change it to 0 to 8. Sorry about that. Let's pay attention and read it right. That would help. There's your 48. So yeah, never want to keep the natural length as anything but 0. So whatever the natural length is, call that 0. And then if we're going to go double the natural length, it's going 8 beyond. It'll get us to double the natural length. Okay. So therefore, that's why it's a 0 to 8, not 8 to 16. Like I said, that integral that we did 8 to 16 would be the work done going from 8 beyond to 16 beyond, basically. All right. Anything else on the practice test?
Number 2.
Number 2, we have some line segments that give us our velocities here. And we want to show where's the particle at the end of the trip. Keep in mind that we're going from 1 to 2 here. We have a segment that starts at 2 and goes up to 2, 3. Okay. So ultimately, the area under that part right there would give us some movement in the positive direction. True? So it's trapezoid here, so its area would be 1/2 times the height would be 2, the bases would be 2 and 3, plus 3 I should write. So ultimately that trapezoid right there would have an area of 5. So that means from 0 to 2 we're moving 5 to the right, if you will. And I don't know if it tells, yeah, it's on the x-axis, so we're moving 5 to the right. So horizontal motion here. The next one though goes from, so it goes from 2, -2. Over to 4, 2. So that means that we have two different areas here. One would be this triangle right here, which would be a 1 by 2 triangle. And this is going through 3 right here. So this is 2, this is 1. So 1 by 2 triangle would be a half times 2 times 1, which would be 1. So ultimately, if we kind of kept track of our displacement here after we're going 5 in the first 2 seconds, and then after one more second, we're going to go -1 for this little triangle. This triangle here goes from, and my scale's out of whack here, but bottom line here is this is a 1 by 2 also, so we'd go +1 then after that for this part. And then for the last part, we're going from 4 to 6, and that's down there at -3. So that means that rectangle area right there is going to be a 2 by 3 rectangle. It'd be a -6 then. If I calculated the areas of all those shapes. Okay. So ultimately, what's my final displacement? My final displacement is -1, and then I add those up. And notice it said that we start at x equals -3. So where am I going to be if I displace -1? And my final distance here, my x of 0 is -3, so my x of 6 is going to be -4, because I'm going to go a total of -1 in terms of displacement. And again, is that -1 my total distance traveled? Of course not, because we're going to travel that much, and then another 1, and then a 1, and then a 6. So total distance traveled, we just add those all up, keeping the negatives as positives. Okay, and that's why in part B, our answer is 5 plus 1 plus 1, that's 7, plus 6 would be 13. So total distance traveled would be 13. What else? Huh?
Number 4.
And 4, we have the top function is the quartic function, isn't it? So wouldn't the integral then be 16 minus x to the 4th minus the bottom function 12 minus 3x squared? So what's the only issue that we have besides that? The limits. So the limits are going to be those x values down there. So how might we find those x values? Yeah, if we set 16 minus 4x, or x to the 4th, let's say, equal to 12 minus 3x squared. Wouldn't that equation right there give us those x coordinates in question where they meet? Okay. And if we do that, the result here, if we got everything on the same side, we get x to the 4th minus 3x squared, and then we get minus 4, 12 minus 16. And it just so happens that this will factor. We get x squared and x squared, be minus 4 and plus 1. We know that that'll give us how many real solutions? X squared equals -1, wouldn't it? So how many real solutions from this one? None. This one, if we factor that, we get x plus 2 and x minus 2. So ultimately, what are our 2 points in question? Be -2 and, not -2, 2 as a point, but -2 and +2. So those would be the intersection points. So that's how we get our limits here. So if we do our integral from -2 to 2, the top function minus the bottom function, we'll get our final answer, which I don't remember what it was. Is this the 500 over 3 one? 96 over 5. Oh, it does say analytically? Well, analytically, like I said, I'd probably rewrite it as this first. Actually, no, so we've got to do the subtraction, I guess. So it would be 4 minus x to the 4th plus 3x squared. So it would be 4x minus x to the 5th over 5 plus x cubed. -2 and 2. So if we put our 2 in there, we're going to get an answer. Put the -2 in there, we'll get an answer. Subtract them, we should get that 96 over 5. Alright, so 8 here, minus 32 over 5 here, plus 8 here, minus -2 in there will give you -8, minus -32 over 5, and this will give us -8 again. So in the parentheses here, we have 16, and these parentheses over here we have -16. So if we did 16 minus -16, that'd be 32. And then with these two, we'd have negative 32, and this would be a plus right here. So it would be minus 64 over 5. And ultimately, if we multiply 32 by 5 to get the common denominator, we get 160. 160 fifths over minus 64 fifths would be exactly what we just said, 96 fifths. Anything else on the practice test?
Number 8.
And number 8, we have a region that is y equals 16 plus x squared, which we should recognize as a half circle. Nope, I lied, that's not a half circle. 16 minus x squared would be a half circle. So ultimately, not a half circle. So let's take a look and see what we got here. So we can set up our region properly, 16 plus x squared. And y equals 5 is the other boundary line here, so let's just take a look at this graph first and see what we got here. So we have that, which comes down here, that. Looks like that goes through 4, 0, 4. Of course, 0 and 4, and there would 0 would make 4. So here's 5, here's the line y equals 5. So that would be our picture, essentially. So we can see the region in question. And it says and for x greater than 0, so it's actually only the right side of that. So you would disregard the left side. It says x greater than or equal to 0. And it says use the shell method to find the volume revolving in this around the y-axis. Okay, shell method would be appropriate here because we could draw a vertical slice, and therefore the vertical slice would be parallel to the revolving line, which is the y-axis. And so if we set up our shells, we're going to go from, we can see 0 to something, 2 pi out here. The distance between the shell and the revolving line in this case is just x. The height of the shell is going to be 5 minus the square root of 16 plus x squared dx. So that would be our integrand, top minus bottom here, to get the height of that shell that I have drawn. And the other issue is, what about this right here? Yeah, we need the intersection point between those two. And so if we drew the y equals 5 on there, and we did our intersection command, we get 3. Which shouldn't be terribly surprising, because if we put a 3 in here, we'd get 9. 9 plus 16 would be 25, and 25 would give us 5. So we just go from 0 to 3, and use that as our integrand, and should be good to go.
They have a different sense of that too.
Then what this shows?
Yeah.
Let's see, I don't think this, it says x greater than 0, right?
Yeah.
So we do only want the one part. So let's see what it gives here. So this would be x times 5 minus square root 16 plus x squared. And that's it, right?
You need another parenthesis.
I missed one.
Close in that 5.
Yeah, you're right. 0 to 3. That gives me that, which is 13.6
Isn't that what they give? 13.
times 2 pi. 26.6 would be 13 thirds. Isn't that what I said? 13 pi over 3?
That's what those guys are.
Good? Alright. Questions on the setup for that one? Anything else?